that I let go. I think I'm a little bit in love with you. But only just a little bit in love with me.
To wrap up chapter 16, I will talk about one application of sound waves, and that is the medical imaging using ultrasounds. Ultrasounds are frequencies that are higher than the human ear can hear, so they are usually defined to be frequencies higher than 20 kilohertz. So, what's the concept of ultrasound imaging? Let's draw some tissues here. So, this could be the abdominal wall. Then we have something else after that. That would be just water, for example. And then we have some organ here. And it's a different type of tissue. And let's say we have a water, some kind of fluid behind that. So we have 4 different areas of tissue. So here's the first one, second, third, and then again fourth. Now let's place a ultrasound probe to our subject's abdominal wall, and we will send ultrasound waves through the body or into the body. So as we do that, the ultrasound just attenuates as it goes through the tissue, but nothing happens until it reaches the boundary between two different tissues. Whenever there's such a boundary, there will be a reflection, and the reflection is due to the different physical properties of these two media. So we have a reflection here where the tissue changes, and part of that sound wave will reflect back. And we have a receiver here next to the transmitter that will receive this signal. And by measuring the time of flight that it takes for this signal to propagate through tissue and then reflect back, we can determine what is the thickness of the tissue. Let's call that thickness D1. So that is just the speed of sound in human tissue, we call it V, times the measured time of flight back and forth, the combined time. So by measuring time, we get the distance, simply by using this identity. Okay, so but whenever there's a reflection, we also have part of the sound wave propagating in its original direction. And now that it's going through the tissue number 2, nothing happens except that the signal attenuates a little bit until it hits another boundary between 2 different tissues. Again, there's a change in the physical properties of these tissues 3 and 2, so we will get a reflection from here as well. So part of the sound wave will reflect back. And we can calculate the distance from the scope to that tissue boundary to be D2 is speed of sound times the measured time of flight back and forth. Okay, so again, part of this sound wave will keep going through the tissue number 3. It attenuates even more until it hits the boundary between 3 and 4. And yet again, we will have a reflection I'll just draw it a little bit lower here so that it's clear. And how far is the boundary between 3 and 4? Again, we measure the time of flight, and that gives our distance. Velocity of the sound times the time of flight. So in fact, if we're precise, this d3 tells the distance back and forth. So by dividing this by 2, we get the actual distance from the scope. But that is taken care of by the computer program or the electronics. Now that we have the distance data of these reflections, we can in fact reconstruct the image. So we have our scope here, and the skin would be here. So now we know that there was a reflection at distance 1, so we have some kind of tissue change at that distance. Also, there was another reflection at distance d2 from here, and also at d3. So this is purely one-dimensional imaging, and as such it's not very informative. But if we move this scope up and down and repeat this process, you can see how we start to get some more information. We can construct the whole tissue boundary there, and we will also probably get the shape of the organ here, and also of its back wall. This can also be extended to 3 dimensions by sending signals from different angles. So that's how you can construct images that look 3-dimensional, or at least something that resembles more the organ that it would look to naked eye, when you can see it from a different perspective at the same time. Now, if you think about this in more detail, I told you that whenever there's a change in tissue, there will be a reflection. So, for example, if we have this wave propagating all the way here, and then it's reflected back, there will also be another reflection here going the other way. And when this reaches this tissue again, there will be another reflection. These signals are much fainter because they travel so much longer in the human body. So, but that's one of the reasons why we get this fuzziness in the ultrasound images. We have the sound waves bouncing around until they die off, and until they do so, they will produce this noise to our image, if you will. So that concludes our treatment of chapter 16. If you had any trouble in the homework, please also see our homework videos where we worked out a selected number of problems.
Hard.